In this video, we're going to talk about a major chunk of the AP Calculus curriculum, and that has to do with something called integration by substitution, which we also call U-substitution. And what integration by substitution allows us to do is it allows us to evaluate integrals that involve function composition. So you might say that it is analogous to the chain rule for integrals. So since this has to do with function composition, let's go back and review what we know from derivatives about function composition. If you remember that the derivative of f of g of x is just f prime of g of x times g prime of x. And if that's true, then what should the integral of that derivative be? Well, it should bring us back to the original function plus or minus some constant. Now, how is that useful for us? Well, it turns out that there are some cases of integrals of function composition that we can now integrate using this strategy or using this concept. And it works something like this. If we were to take the inside function, which is g of x, and set that equal to u, then we took the derivative of both sides, or took the derivative of u with respect to x, then we would get du dx is equal to g prime of x. And if we solve for du, now if you notice back in the original integral of f prime of g of x times g prime of x dx, we now have g prime of x dx is equal to du. And if g of x is equal to u, we have now simplified that big long expression f prime of g of x times g prime of x dx down to just the integral of f prime of u du. And so we're looking for the antiderivative of f prime of u. We're looking for the function whose derivative is f prime, and that should just be f of u, not to be mistaken with fu. And of course plus c. So it almost looks vulgar there, f of u plus c. And so that's how we're going to, then we're going to swap back out the u, which is equal to g of x. And in essence, what we have is we have a technique, a computational technique now that allows us to go from this complex integral to finding its simple antiderivative. So let's take a look at an example of what this might, how this might work. Well, in the Larson 7 book online, chapter 4, section 5, we have this exploration at the beginning of that section, which includes 6 different integrals. And we want to take a look at them. If you notice, they all look very complicated. None of them could be simply simplified by multiplying them out and solved as an integral of a sum or difference using the sum or difference rule. So I'm going to do one of them on this video and do the others in the next. Well, in order for this technique to work, a couple of things have to be in place. First of all, ordinarily, not always, but ordinarily we're going to have some kind of function composition. For example, f prime of g of x. So we have some function composition. Not only so, but the derivative of that inside function is multiplied times the function composition. So when we have that, what we're going to do is let the inside function be our u, and then we're going to start the u substitution process. So when you have function composition, such as in A, in the exploration below, notice that we have x squared plus 1 quantity to the 4th power, where the inside function is x squared plus 1 and the outside function is something to the 4th power. Then, not only so, but the derivative of that inside function, which would be 2x, shows up on the outside of the function composition, or is multiplied by the function composition. And when that's the case, we let the inside function, which is x squared plus 1, become our u. Taking the derivative, we get du dx is equal to 2x. Solving for du, we get du is equal to 2x dx, which we can then swap out in the original integral. And the x squared plus 1 is just u. So now that whole thing just becomes integral of u du, which is u squared over 2 plus c. And substituting x squared plus 1 back for u, we get x squared plus 1 quantity squared over 2 plus c. And we're done.